Good afternoon. I am Andrew White, Business Development Manager for Valve and Valve Automation with the Lessman Instrument Company. Thank you for taking the time to attend our webinar this afternoon. Our topic today is Advantages of the Jordan Sliding Gate. This webinar will be recorded and posted to our website for anyone to view at a later date. Please enter your questions in the questions section of the menu bar, and we will answer those at the end of the presentation. I'm pleased to announce the speaker for today's presentation, Matt Lansdale. Matt has been an integral part of the Richards Industrials team since March 2020, serving as a skilled inside sales specialist based in Cincinnati. With a robust background in sales and a deep understanding of all product lines offered, he covers a wide range of territories around the globe, including Lessman Instrument Company and the greater Chicago area. Matt, you may begin your presentation.
Thank you, Andrew. And thank you for everybody who's taken the time to watch this. Like Andrew said, we are going to be talking today about the Jordan Sliding Gate and its advantages against a traditional globe-style valve. So in this presentation, we're going to cover three main points: the design of the sliding gate, the materials that we use to make the sliding gate, and the performance of it. The sliding gate is an alternative to the traditional globe style valve. We offer it in PRVs, pressure regulators, back pressure regulators, temperature, and control valves. They were really designed for use on steam, but they are used all over the industrial process world, in steam, air, oils, gases, water, you name it. There's a few basic designs. The first two listed here are essentially the same. It's a full body valve with a body and a cap, the sliding gate there in the middle. We make them in smaller sizes, inch, half inch, 3/4, 1 inch, and we make larger versions with larger CVs. And one of the advantages, we offer a wafer style valve, which is a much smaller profile than a traditional globe style valve. It pretty much slides right in between two pipes, and there's some pictures on this slide here of some wafer style valves and their small footprint. So the design of these sliding gates, if we're looking at this kind of exploded view, it looks more complicated than it actually is. It's really three main components. We have the disc that is the moving component to the seat, the plate, which is stationary, and the disc guide that keeps the disc centered as it travels up and down. Like I said, the disc guide, it creates the seal between the body and the cap, and keeps the disc, which is in the center of this little exploded view. It's that square piece right in the middle. It keeps that centered as it rides the plate to open and close the seats. So, like I said, the valve disc is the moving component in the set. We can make this in a variety of sizes, orifice sizes, CVs, and there are a few flow characteristic options we have, but the one we have pictured here is by far the most common. It's a linear characteristic. The valve plate is the stationary section of the valve, or of the seats. The disc is coated, and we'll talk more about the coatings that we can put on these seats. The plate is typically uncoated. It's chrome plated in either 303 or 316 stainless steel. We can make these seat sets out of different alloys, Inconel, Monel, Hastelloy, if your application dictates that. But 303 and 316 stainless steel is by far the most common. The stem will actually connect to the disc through the plate, and the plate stays stationary, and it pulls the disc. The stem will pull the disc up and down across the plate to create the seal or open the valve. So this is essentially the same thing I was just talking about, but the way that these go together, the plate is in a PRV. The plate is typically on the outlet side, where it's downstream, and the disc is upstream. And what's great about the sliding gate is as your media pushes through the valve and onto the seats, it actually creates a tighter shutoff as the media is pushing the disc into the plate harder and harder. Same thing here with our larger size bodies. It's the same function as the smaller sizes. We can make these in a number of CVs, from very low CVs, fractions of a CV, to 1 to 300 CV. So like I mentioned at the top of the presentation, one of our great benefits to the wafer style and to the sliding gate is this wafer style valve. It's way less metal involved than your typical full body valve and globe style valve, which directly impacts the budget, right? It's less metal, it's less expensive. The footprint's much smaller, means it weighs less. But the design is essentially the same here. The disc guide is a little different, as it's on the side instead of on top of or around the disc. But they are essentially the same, just in a more compact drop-in format. The seat materials we use, like I mentioned earlier, typically it's 303 or 316 stainless steel. We can coat the disc. Our standard seat material is our proprietary Jorcote coating, which is extremely hard. It has a lower coefficient of friction than Teflon. We can do Teflon seats, and we really only see that in oxygen services, but Jorcote is the standard. Jorcote's 3 times harder than stainless steel. Like I said, the lower coefficient of friction than Teflon. Jordan Valve had Jorcote tested, lab tested on 70 psi steam to 1 million cycles, and it still functions to that point. It is a long-lasting, much better performing material than a metal-on-metal seat, which can be done, but Jorcote's really advantageous over metal-on-metal. Again, Teflon available for those special circumstances in an oxygen-rich environment. We don't always want to use Jorcote, as it has the possibility to spark, which would be bad in a oxygen-rich environment. So Teflon's an option, or if your specific media might call for it. And like I mentioned earlier, we can do the trim in a number of alloys, depending on whatever it is that you may need. So what makes the sliding gate better? There's quite a few things. You get the straight through flow, a short stroke, where most globe style valves can stroke, from full close to full open, 1 inch or 2 inch. Most of these sliding gates are going a 1/4 inch, which is just way less wear, less moving parts, much better performing. So where the seal is made, which I believe we'll talk about here in a few slides, the disc and plate overlap by 1/32 of an inch to create the seal. Very easy to maintain. The seats are constantly in contact, so it pretty much eliminates chatter. There is no lifting off of the seat and reseating. These seats are always in constant contact, rubbing against each other. So it pretty much eliminates chatter. So like I said before, as the media pushes into that disc, it creates a tighter seal. The straight through flow is great in a sliding gate, as it eliminates a lot of the turbulence coming out of the valve. If you see the lower illustration there of a typical globe style valve, with the tortuous flow going through the valve body, your media turns 3 times before it exits the valve. Those turns are eliminated in a sliding gate, which allows your media to settle downstream back into that flow as it entered the valve much quicker and in a shorter distance. Because these seats are in constant contact, they are always self-lapping. They wear in, as people here like to say. They don't wear out. They're always lapping together. They're always touching. So they just get better over time with their sealing, and they clean themselves. I've seen sliding gates be used in some slurries because it's got that shear force as it opens and closes. It will clean itself just in normal operation of the valve. Like I mentioned earlier, the stroke on a sliding gate valve is much shorter than your typical globe style valve, which directly impacts how fast it responds, because the stem doesn't have to move as far. If you're using a control valve or an air-loaded regulator, it's much quicker to react. Even the self-operated valves are much quicker to react than the traditional globe style valve. And because that stroke is so much shorter, there's less wear on your diaphragm, because it's just not moving. It's not flexing up and down quite as much as some of the traditional style valves that have a much larger stroke. That those diaphragms really have to bend and flex up and down much farther than in our valves. So part of the flow through design and the less tortuous flow, impacts the noise. It's much quieter than a typical globe style valve. Like I said earlier, it dissipates the flow downstream much quicker. Now, the last point here, that it resists damage to cavitation and flashing. In a globe style valve, if your media is going to cavitate, if you have a water application and it's cavitating, it can eat the valve up. In a sliding gate, that's all going to happen past the seats, and especially in a wafer style valve, it's going to be downstream of the valve. So it's very common for an application that has this issue, for somebody to put a sacrificial piece of metal right after the valve for the cavitation, and really is better on the valve's life with the cavitation and flashing versus a globe style valve that just can't get rid of the cavitation, or can't, it happens in the valve besides past the valve. So talking about the constant contact of the seats, like I said, there is no lifting and then reseating, so it doesn't chatter. There's less wear because of that. Self-lapping, self-cleaning. These valves are machined and lapped here at the factory so well that you can actually push the disc and plate together and they will just stick together due to friction. That's how well they're lapped together. So here's a good little illustration of the overlap where the valve seats. It's not a line of closure like a plug into a seat. It's an area of closure with this overlap. So in a globe style valve, if you get a nick or a scratch in your seats or your plug, it can you can have media get through there and really kind of defeat the purpose of shutting the valve off. In a sliding gate, given the overlap area of the seats when the valve is shut off, it's much more resistant to those kind of blow-throughs and damage to any kind of seat that the valve might see. It'll still shut off. One of the great things about the sliding gate is the ease of maintenance. Some of these pictures make them seem complicated, but they're really a simple. They're simple devices. They're simple parts. There's very few moving parts. It's very easy to change CVs in and out if your application changes and your flow rates change. It's very easy to open a valve and put new seats in. It can be done in the field, and it's relatively easy to change the control valve action in a sliding gate if it's going from reverse to direct or vice versa. In, I believe, the Mark 80 temperature regulators, it could be as simple as opening the valve and turning the seats 180 degrees, and that will change the action of the valve that simply. And a quick little summary. Ease of maintenance, size and weight. We have a valve that's hanging on the wall downstairs here at the factory. It's hanging on a plaque on the wall because it was in service for 50 plus years. The customer called us looking for a new one, and when we found the old paperwork, they bought the original valve 50 years prior. So like I said, they wear in, They don't wear out. It's a much longer, better performing valve. I also wanted to speak a little bit on our proprietary diaphragm material, the Jorlon diaphragm. It is a modified PTFE proprietary blend of Teflon-like product that is almost bulletproof, to put it as simply as I can. It flexes much easier than a Teflon or other elastomers. Excellent at high temperatures, pressures. It is very compatible with a number of chemicals. We like the seats. We had the Jorlon diaphragm tested and compared it to a kind of standard industry standard stainless steel diaphragm. At 225 psi steam, the stainless steel diaphragm failed right in and around 1300 cycles. We stopped the test on the Jorlon over 250,000 cycles in, because it wasn't gonna stop. Same at a high pressure test on steam, between 360 and 430 psi. We stopped at around 125,000 cycles with no failure. So there's a video here at the end of our presentation that I believe the presentation is going to be made available after the fact. I won't spend the time here and now to play it. It's also available on our website, but it's an illustration of how the seats go together and operate. So I thank you. Andrew, thank you very much.
Yeah, thank you, Matt.
Any questions?
Yeah, I think we've so far just got one question right now. A viewer asked, can I buy just a replacement disc or plate separately if one of them are damaged?
So typically no. They're really a seat set, and like I mentioned earlier, with the seats being lapped together to a high degree of precision, they're really a seat set. You want your plate and disc to be a pair. They get lapped together here at the factory. So it is a seat set that you would need to get to replace some seats or switch them out. It's fairly easy to do.
Okay, I appreciate that, Matt. Last chance, any other questions we have for Matt before we let him go today? Okay, looks like you did a great job. Not many questions here. So thanks again, Matt. Appreciate your time today, and thank you to all the people that are viewing the webinar. Look forward to our next announcement for our next webinar in August that we'll be doing, and thank you all for attending. Have a good evening.